In this video, we are going to create a heat exchanger based on this datasheet. We click on the Add New Vessel button to begin. Here we enter the initial vessel information like name, service, operator, etc. We select Shell and Tube Heat Exchanger vessel type. We select both the shop and site test hydrostatic tests with corroded condition on site test. Finally, we select 1.5 mm minimum thickness of shell. Now we proceed to the Process Data tab. Here we can see that there are 3 different process cards. There is the shell side process card, the tube side process card, and the combination of shell and side process card, which gets its data from both aforementioned process cards. Now we enter the data for the shell side process card first. The value of TS max at external pressure doesn't really matter, as we are going to calculate the heat exchanger based on internal pressure only. Now we enter the data for the tube side process card. Here we can see that the data for the combination of shell and tube side process card has been entered automatically. This combination process card is used automatically for specific heat exchanger components, such as the tube bundle and the floating head. Now we move on to the Vessel Desktop tab and select Cylindrical Shell to add the main shell. We enter a simple name and description and proceed to the Design Data tab, where we select the process card input chapter. Here we can select whether to use the shell side or tube side process card. We will select the shell side process card for this example. We select Internal Pressure Only on the Pressure Loading option. We move over to the Shell Data input chapter. We select Seamless Pipe Fabrication and continue to the Shell Geometry Data input chapter. Here we will use the pipes library to enter our data for NPS equals 18 inches, wall thickness equals 9.53 millimetres. We input 5,716 millimetres for the length of the shell. And move on to the shell material data input chapter. We add the SA106 GRB material to the main shell through the Advanced Search tab. And finally, we move on to the Component Liquid input chapter. We click on the Full button to completely fill the shell with liquid. We save our main shell by clicking on Calculation Details. Now that our main shell is complete, we exit back to the vessel view in order to add our next component. Now we will add a flange to the vessel. We enter a name and description for the Tubesheet flange. And move on to the Component Attachment tab. Based on our datasheet, we select to attach the Tubesheet flange on point 5716 on the X-axis. Now we move on to the Design Data tab. We select the Process Card's Input chapter. And select the Internal Pressure Only and Shell Side options, just like on the main shell. Moving on to flange data, we select Appendix 2 for the calculations and User-Defined Flange on the Flange Standard. Notice that for User-Defined Flange, the flange hub type is automatically set to Loose Hub and relevant flange type options open accordingly. We select Integral Hub Flange and Sketch 6 at the flange type, where more options are available. From flange options, we choose to apply bolt spacing correction factor. We move on to the flange geometry data input chapter. We enter the data for outside diameter of flange. We assume that known values are B, G0 and G1. In order to keep dimension B stable and input G0 and G1, we need to click on these specific dimension input boxes so that the blue buttons appear on B and GO, G1 respectively. We input 437.94 millimetres for B. We input 9.52 millimetres for G0 and 18.92 millimetres for G1. We input 535 millimetres for bolt circle diameter. And input 28 for the number of bolts. We also input 50 millimetres for flange thickness. And finally 35mm for hub height, resulting in 85mm overall flange height. Now we will input the modulus of elasticity, which is used for calculation of flange rigidity. We select the first option for carbon steels. And we move on to the flange exterior forces input chapter. Once the mating flange is calculated, channel flange on Tubesheet, it is proper to revisit this flange and consider the loads from the mating flange which may govern design. And we move on to the flange gasket data input chapter. We select the soft steel jacketed gasket material from the list of gasket materials. And we see that the gasket factor and minimum design seating stress have been filled in automatically. We leave the facing sketch as it is, typical. Now we input the flange gasket outside and inside diameter. We see that the gasket width has been calculated automatically at 13mm. We input 5mm for groove excess thickness. This thickness is not used in flange verification, but it is used for calculating the flange weight. Now we move on to the flange bolting data input chapter. We select the 3/4 inch size bolts from the library. We move on to the flange material input chapter. Using the Advanced tab, we select the SA266 material. We select Grade 2 and click on Use Material to finalise our selection. Bolt material is pre-selected as we want. Typically, this material is automatically selected by software based on component attachments. But in case the user needs to specify it on their own, uncheck the Use Shell Nozzle Material checkbox. Similarly to the main shell, we click the Full button to fill the flange with liquid. We click on the calculation details to save the flange. We exit back to the vessel view. And click on the 3D button to view the first parts of our heat exchanger. Here we can see our heat exchanger so far, filled with liquid in dense blue. The first step in making a heat exchanger is complete.